Hello and welcome to this WebEx presentation video. This is the fourth WebEx that is due for Senior Design 2. This is the WebEx posting that is due Friday, March 28th. And it's the WebEx for the Temple University NASA Lunabotics 2014 electrical team. My name is Mark Halberstadt, and on the team with me is Eric Schisselbauer and John Morris. And myself and John are going to walk you through this presentation. So in this presentation, I'm going to go over our electrical team goals, show the overall progress that's been made, and specifically this is the overall progress that's been made since the last WebEx update, and then I'm going to talk about what the next steps are for the project. So the electrical team goals have not changed since the beginning of this project. The first goal is to design and build power control and communication systems capable of piloting a mining vehicle through a harsh lunar environment. Our second goal is complete autonomous functionality of the mining vehicle, and our third goal is increased power efficiency of the power system and really the entire electrical system in order to reduce the size and weight of our battery, or to at least explore the option of reducing the size and weight of the battery. So the overall progress that we have made since the last WebEx update has been we have 3D printed a new pole for our beacon that is going to be locating the robot. So, and I'm going to be showing you photographs, and actually John is going to walk you through some of the construction and the ideas for that beacon. We've attached all of the LEDs to this newly printed beacon, so it's actually, and we've tested them, and it's actually working really quite well. We've implemented on the autonomous system a path planning algorithm for pretty much planning a path for the robot through the obstacle field. And also, we have implemented a motor speed calculator based on the location of the robot and the path planning data generated by that path planning algorithm. So later on in the presentation, I'll have a video that kind of shows how the path planning algorithm works. And I'll probably talk a little bit about how the path is being computed, how the path is being simplified, and also how motor speed is being calculated based on that path. So now I'd like to turn it over to John, and John is going to be presenting some photographs we have of our new beacon pole. So, John?
Yeah, so this beacon right here is actually an infrared beacon. There's a little bit over 300 LEDs on this beacon. They're all infrared. The way it's divided up is there's 14 strands, as you can see on the I guess the bottom 3/4 of this. There's 14 strands that go all the way around. They're divided up into 14 channels, which are actually you can see the Cat 5 cables coming out the bottom. One of the cables on the one side is for one half of the beacon, and the other on the other side is for the other half. Then, of course, we have the rings on the top. These top 4 rings are divided into 2 channels. So the 14 around the lower 3/4 of it, and then the rings on the top. That's all 16 channels total, and that's pretty much it for the beacon.
Yeah. So we've also, like, one of the reasons, I guess, for 3D printing the beacon was so that we could get a much more exact fit for the beacon to go on top of the linear actuator. One of the things about the competition, we are required, the maximum height that we can have on our robot is 75 centimeters. We can only extend from the bottom, from the absolute bottom of our robot up to the top of our robot at the start of a round. Can not exceed 75 centimeters. So 75, the top of the robot right now is right at the top of this motor enclosure, motor system that we have right here, and that is at about 74 centimeters. So we're pretty close to our limit. And the position, this is an antenna for the robot, the position of that antenna is going to change. But we're really pretty close to our limit right now with the top of the robot. So what we need to do for the beacon, because in order for the location system to work, the beacon really has to be the highest point on the robot, is we needed to put that beacon on an actuator such that when the competition round begins, the actuator extends up beyond that 75 centimeter limit, which is allowed in the competition. We are allowed to extend up to 1.5 meters. We extend the beacon up, so the beacon will now be the highest point on the robot, and the location system will be able to easily see that beacon. And one of the reasons for 3D printing it was so that we could achieve a very snug fitting, a very exact fitting for this beacon onto this actuator. Another reason we printed the beacon was so that we could pretty much mount our compass unit inside of it, and the compass unit could be held very precisely at a, either pretty much perpendicular to the facing of the robot. So the beacon itself wouldn't be moving around a lot. The beacon has not been mounted inside of the pole yet, but we do have the indentation in the beacon in the newly 3D printed beacon, and we're going to be gluing it in. So we are really confident that this design is going to help keep the compass unit fairly stationary. So anyway, that is everything for the beacon. Now I want to move on to just a short video demonstration of the location system working with the path planning system. So I'm going to play that right now.
Hello and welcome to, I guess, this presentation on the progress that is being made on the autonomous system for the Lunabotics project. So the progress that has been made is, let me just, I guess, show you what exactly is going on here. I have got two of these Rocket brand Wiimote object tracker modules wired up. And I also have the 3D printed version of our beacon wired up, and it's fixed onto a tripod. And right now, this is over a wired connection. We have a wired connection with the beacon, so this currently is not operating over a network. But I have these devices wired up. They are providing location data back to our autonomous system. And as you can hopefully see from this screenshot, I just got in the way of it. A second, there, it's located again. So as you can hopefully see from this screenshot, that location data is being used to compute a path of best fit through two, I guess, kind of virtual obstacles that we have in our arena. So anyway, that is it. That's kind of the progress that we've got so far. Anyway, thanks for watching, and yeah, I guess watch for more videos to come. Thanks for watching.
Okay, let me just go ahead and I want to just highlight a little bit this path that's shown in the video, and I'm actually going to blow it up a bit. So pretty much what is happening here is we have two virtual obstacles that we have placed in our arena. One of the things that you might be able to see is that the obstacles that we are placing in the arena are going to be implemented as essentially circles. We're going to give them a given radius, and that is how we're going to be putting them into the arena. And then we are able to compute a path, and this is actually the shortest path using an A-star algorithm. We're able to compute the shortest path that navigates the robot through these obstacles. So one of the things that we are doing, so we get an A-star generated path, which is essentially a pixelated path that only moves at right angles. And then we use an implementation of Brazenham's line algorithm in order to simplify that path. Pretty much what we do is we split the path in half, draw a line between two of the points, and determine whether or not that line intersects an obstacle. If it does not intersect an obstacle, we can delete all of the points in between those 2 points. However, if it does implement an intersect with an obstacle, we split the path in half again and rerun the algorithm. So it's a recursive algorithm, and as you can see, it ends up simplifying the path very well. So this is something that's going to be easy to implement on the robot. So anyway, that is it for the video demonstrations. For the next steps in the project, for the power system, we are going to use the power system to measure current provided to the dig and dump motors. Our mechanical team is receiving in very shortly a new motor for the dump system. And we are going to have to measure the current that we are supplying to that motor to make sure that it's within our power system specifications. For the communication system, we're going to be constructing network Java packages for the autonomous system and the location system. And for the autonomous system, the next step really is integration of the autonomous location system, the path planning system, and the autonomous GUI monitor over a wireless connection. Right now, we do have all of that stuff integrated together. However, it is over a wired connection. And it's also all running on the same computer system. And we are actually experiencing some problems right now. The way the location system and autonomous system was essentially built, they were not intended to be run on the same computer. So we are trying to, we built them with the intention of the fact that they would be running on separate machines and those machines would be networked together. So the next steps for the autonomous system is really to achieve that, to implement them on separate machines and then network them together. For the schedule, as of April 1, we should have finalization of all the network software for integrating together those separate machines for the autonomous system. And by April 3rd, we may have our first autonomous test on April 3rd. We're still waiting to hear back from our mechanical team to make sure that they're ready for their autonomous for another test, and also the location where we have been doing these testings. We have to check to make sure that they will be ready. But by April 3rd, the electrical team should be ready for our first autonomous test using the actual robot that we will be competing with at the competition. So anyway, that concludes this WebEx presentation. Thank you so much for watching, and if you have questions or comments, please feel free to leave them in the video or send an email to me at c.mark.halberstadt@temple.edu. Thanks so much for watching.